Shri Gurubhyo Namaha. Welcome to our online learning initiative Ekalaiva. I am going to explain about AC voltage applied to a resistor. So, let us consider the AC supply voltage. We know the symbol for AC source. So, this is the symbol with which we will represent AC source, which is connected to a resistor. So, we are going to connect only resistor. So this is the AC source which is connected with resistor, children. Okay. And we know that how will you represent this AC voltage. So in the previous topic itself we discussed that V is equal to Vm sin omega t. Right. So V is equal to Vm sin omega t. Okay. And we know that Vm, which is nothing but amplitude of the oscillating potential difference, and omega is its angular frequency. And now we are going to apply Krichov's loop rule. So when we apply Krichov's loop rule, so let me write here, children, applying Krichov's. Hope all of you remember this Krichov's loop rule, whatever we discussed in current electricity. Krichov's loop rule. To this circuit, we will get Vm sin omega t is equal to I R. So first let us consider this is our equation number 1. Okay. So can we write this I is equal to bring this R to the denominator here, Vm by R sin omega t. Okay. And what is the current amplitude? Let us consider the current amplitude Im, okay, is given by Im is equal to Vm by R. So can we write this as that is Im is equal to Vm by R. Okay. So I is equal to Im sin omega t. Okay. So this is very important, children. So this is our equation number 2. So actually, what is the voltage across a pure resistor? V is equal to Vm sin omega t. Similarly, the current through this resistor as I is equal to Im sin omega t. Now, we are going to plot the graph for this voltage and current as a function of time. Okay. So, when we draw the graph, actually the graph will be drawn for this voltage and current as a function of time. Okay, so first let us have this is our omega t. So I am going to draw the graph for voltage first. Okay, so voltage as a function of time. So this is the voltage. Okay, so voltage is this, and this is V M. Okay, and let me write 0, pi, 2 pi. Okay, likewise we can write. So actually this point will be, that is B. This is B. Okay. So now let me draw current in other color so that it will be easy for you to distinguish, right? So current. So look at the thing here, children. This is very, very, very important actually. Okay, so let us state this is I. And what is this? IM. Okay, so actually, when you see this graph, what is the conclusion? What is the significance? We can say that that is at in a particular time, that is B and I. So look at these two things. When B is 0, I is also 0. And when this B reaches maximum, I also reaches maximum. And again when B is minimum, I is also minimum. So what is the conclusion from this graph? We can say that voltage and current. Okay, voltage and current. Voltage and current are in phase with each other. Voltage and current are in phase with each other. So this is very, very, very important. Okay, because we know that B is equal to Vm sine omega t, and similarly I is equal to Im sine omega t. So when we connect the resistor across this AC voltage, you will get that is V is equal to Vm sine omega t and I is equal to Im sine omega t. And what is the conclusion? I told you voltage and current are in phase with each other. Now, let us also calculate what is the power in a purely resistive circuit. Okay, what is the power in a purely resistive circuit? We see that like the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of the instantaneous current values over complete cycle is 0 and the average current is 0. Here one thing is very important, children. The average current is 0. It doesn't mean that the average power consumed is 0 and that there is no dissipation of electrical energy. Okay. So here, which is what is very important, average current is 0. But average power consumed, which is not 0, and we cannot say that that is no dissipation of electrical energy. Okay. And as we know that Joule's heating effect is given by, so you are familiar with this formula that H is equal to I square RT, right? So according to this Joule heating, okay, so here we are going to consider this Joule heating. This Joule heating is given by I square R. So which depends on, so here this is again very important. depends on I square. Okay, it depends on I square, not simply I. So whether this I is either positive or negative, okay, this will be always positive only. Okay, so you can say that there is a Joule heating and dissipation of electrical energy when an AC current passes through a resistor. Okay, so it depends on I square. So first, let us consider what is the instantaneous power dissipated in the resistor. Okay, so the instantaneous power dissipated in the resistor is P is equal to I square R, and already we know that what is this I? I is nothing but I am sine omega t, right? So we are going to substitute it here, children. So already you are familiar with that. So sine square omega t, and now let us calculate what is the average value of power over the cycle. Okay, so the average value of power over a cycle is, so we can represent as this P bar. Okay, so what is this P bar, which is nothing but average value, and this will be written as, that is like this bracket. Okay, I square R. So again, this which indicates that average of the quantity inside this bracket. Okay, so normally we will represent like this. So this is equal to, and we know that I square R sine square omega t. Okay, and we are going to see what is this I square mr. These two are constants. So these two, since these two are constants, okay, and r, these are constants. So can you write it as either this P bar can also be written as capital P, whatever it is. Okay, so P bar, or else you can write capital P. This is equal to R. So average value of sine square omega t. Okay, so now here this is very important, children. We are going to use the trigonometric identity. Okay, so when you use a trigonometric identity, using trigonometric identity, this sine square omega t, which will be written as 1 minus cos 2 omega t by 2. So already we have discussed this even in RMS value also. So this average value of this sine square omega t. Okay, so how are you going to write this? 1 by 2. Again 1 minus, take this 1 by 2 alone out. So 1 minus cos 2. So for this we are going to find again cos 2 omega t, average value. Okay. So actually, this average value of this cos 2 omega t is 0. Okay, again we will use that integral integration. That is, when you integrate this between the limit 0 and t over the complete cycle, this value will become 0. Okay, so cos 2 omega t, this value which is 0. So then what will you have remaining then? This average value of the sine square omega t is simply only 1 by 2 alone. So let us consider this as sine square omega t. This average value is only half. Okay. So when you substitute this value in our average power, so what will you have then? P is equal to I square m r into 1 by 2. Am I right? Yes, into 1 by 2 alone we will get. Okay, so you can also write that half I square m or whatever it is. Okay, so in order to express AC power in the same form as DC power. So what are we going to do here? So I'll write here. So please remember this average power. Okay, power in a purely resistive circuit is 1 by 2 I square m into r. So in order to express this, we know that that is in terms of that RMS value or something. So I is equal to RMS value. I is equal to Im divided by root 2. Hope all of you remember this one. Am I right? Or Im is equal to, can you write it as root I, children? Yes. Root, sorry, Im is equal to root 2 into I. am sorry. I is equal to Im by root 2 or Im is equal to root 2 into I. Okay. So we are going to write this as P is equal to I square R. Okay. P is equal to I square R, or we can also write that is P is equal to IR into I. Okay, or else can we write it as VI? Yes, because we know that IR is nothing but V. So the average power or true power over one complete cycle of alternating current is the product of virtual voltage and virtual current. Okay, so the average power or true power. Okay, so the average or true power over one cycle of alternating current is over one cycle of alternating current is the product of virtual voltage and virtual current. Okay, and now let us represent this variation of instantaneous power with time. Okay, so how can we represent actually? This is graphical representation, children. So let us consider this is Vi. Okay, and time. So this is nothing but variation of power with time in a purely resistive circuit. A purely resistive circuit. Okay, so this is the graphical representation of variation of power with time in a purely resistive circuit. Okay, so here we can say one thing, children. The power is consumed at all times except when V and I are 0. Okay, and we can also notice one thing here. Actually, Vi remains positive even when both V and I are negative. To receive our online lessons, please press the subscribe button and you will receive the latest updates. Thank you, students.